Good evening. Thank you for being here. I'm Jungmin Kim, a doctoral student at Seoul National University, Korea. And what I'm going to talk about today is the neural network-based design of tunable multilayer films. So here is the content of the presentation. Let's begin with some brief introduction to engineered disorder, which will be one of the keywords of my presentation. As you already know, light behavior strongly depends on the structural information of materials in terms of light-matter interactions. That is, crystals and uncorrelated disorder show distinct features in light propagation, scatterings, and spectral responses. For example, crystals lead to photonic bandgap at a certain range of frequencies, while also allowing efficient photon transport at the other range of frequencies. On the other hand, uncorrelated disorder results in Anderson localization as shown here, or spectrally broadband scattering and the annihilation of bandgap, all of which are distinct from those of crystals. Notably, the conventional transitions from crystals to uncorrelated disorder, which is based on homogeneous, Poisson-like, and isotropic deformation, result in the gradual change of light properties from crystals to uncorrelated disorder. However, due to almost infinite degrees of freedom in structural deformation, there are many possible paths connecting crystals and uncorrelated disorder. So, in this sense, finding a path having both crystal-like and disorder-like physical properties, as shown here, corresponds to the engineering of disorder. There are some examples. First, the structure here looks very disordered, but it is engineered so that its structural factor in K-space resembles that of perfect crystal in the long wavelength limit, which result in the bandgap-like responses. This is called the hyperuniformity defined by Professor Tokiyato. Second example shows disorder-like Gaussian localization in the regime of homogenization, so-called effective media theory. So the question is how to deal with such high degrees of freedom in disorder structure. Conventionally, research has focused on simplifying them with representative function or number for disorder, such as structure vector Sk or translational odometric tau, and then finding a relationship between such metrics with their wave properties. But recent advances in a data-driven deep learning approach enables the direct mapping between numerous degrees of freedoms and their wave responses. So, in addition, neural networks can even avoid some issue regarding one-to-many relationship between response and structures by layering neural network architecture as shown here. So a network like this connecting the response space to response space again has a one-to-one relationship for sure, and it is trained in such a way that its intermediate layer is converged to one possible design among many options, which provide the inverse design from target responses. Many groups have already applied machine learning and deep learning to various practical and theoretical problems in the field of material science, including the inverse design of metamaterial structure using deep learning, or finding scale freeness in inverse design disorder structures, or extraction of underlying physics using autoencoder, and unsupervised learning of topology of materials. So in this work, we demonstrate the inverse design of disordered structures with tunability, which requires high degree of freedoms and which can be resolved by deep learning networks. This is our platform. We have binary multilayer structures, including a core layer of phase-changing material, such as germanium antimony telluride, so-called GST. Then the on-off operation by changing the phase of GST, as shown by blue and red color here, changes the angular response of the system. Then we construct neural networks in both directions. First, from geometry to response space, say G2RNet can infer the response from structures, and in reverse directions, response to geometry space, R2GNet can inverse design a disorder for target responses. Here are the details of the dataset and training information, but let me briefly explain it. First, we diversify the disorder structures by setting their range differently so that we can obtain the various shape of responses as shown here. And then we shuffle all the samples and divide again into training, validation, and tested dataset with total 2 billion realizations. We also use fully connected architecture with batch normalization and gel activation. The inverse design procedure is shown here. First, we define arbitrary target functions for on and off states, and using the target functions as an input to the R2GNet, we obtain the thickness of multilayers as output. And finally, we examine the result by comparing the target responses with the true responses calculated from the transfer matrix method. As seen in these figures, the target and designed responses show excellent agreement, verifying that the designs using networks can be useful even in the active region. These are two examples for the inverse design of optical functional devices. The first one is angle selective switching device with target responses defined by Lorentzian shapes with different center angles. And the second one is broadband switching devices with almost flat target responses except near the 90 degrees. Of course, lines and symbols here are also well matched. These two figures clearly show the operations of the examples. White solid lines here indicate the boundary of the devices in the air, and white dashed lines here especially indicate the boundary of the GST layers. So cylindrical wave is excited from the line source at the origin, and when the devices are turned off, left device transmit the wave in the direction of 30 degrees, and right one transmit the wave in broad range of angle. When the devices are turned on, then left one steers the wave in the direction of 60 degrees, and the right one blocks whole angle component of the incident waves. While we showed specific examples in the previous slides, now let's talk about more general concept regarding the classification of disorder. As mentioned before, the conventional approach in classifying the disorder is basically from its material properties such as structural factors or order metrics. In contrast to this idea, we define a new metric, controllability, by the root mean squared differences between on and off state responses. The important point here is that this is wave property, not a material property. So using modified networks with this single metric instead of angular responses, we can generate multiple realizations or having specific target controllability. For example, the top panels here show the distribution of generate realizations of for controllability 0.05 or 0.3 or 0.6, and then the center panels are corresponding responses, and the bottom figures show the deviation of the true design controllability from the target value with very high accuracy. In this sense, it can be said that the disordered structures here are classified with distinctive metric eta, and is in the perfectly opposite side of the conventional classification. So finally, the conclusion section. To summarize, we applied deep neural networks to the photonic multilayer problems, and we inverse designed the active functional devices such as angle selective device or broadband switching device, and we demonstrate the DNN-enabled classification of disordered structures, especially in terms of controllability. So in future, we are going to reveal hidden mechanism of on-off transition using DNNs, or we are gonna further extend to engineer disorder with higher degrees of freedoms. So this is the end of my presentation, and thank you again for your attention.